Welcome back to our series on probability theory. I'm Mark Ledbetter, and this is lecture video 18, and we're going to talk about the binomial distribution. Last time, we learned how to use the moment generating function to generate moments, such as e of x squared, etc., by taking the derivatives at 0 of the moment generating function. So in this section, we're going to learn the binomial distribution. We're going to learn and derive its mean and variance, and we're going to learn what its moment generating function is and do an example. So a Bernoulli trial is a random experiment, and the outcome of this can be one of two categories that are mutually exclusive and exhaustive. In other words, they're complements of each other. So if you're in one category, you can't be in the other. And if you're in the other category, you can't be in the one. And those are the only two choices that you have. We could say success or failure, life or death, non-defective or defective. So the binomial distribution occurs when we have a sequence of independent Bernoulli trials. And the characteristics of a binomial distribution is that there are two categories. Now, we can have more than two categories, such as freshman, sophomore, junior, senior, but those can be made into two categories. We could say, I'm interested only in seniors, so you're a senior or you're not a senior. Or I could be interested in freshmen. You're a freshman or you're not a freshman. So we're going to classify it as two categories. Even though there may be more categories possible, we're going to treat it as if there are only two categories. So there has to be a fixed or known number of trials or outcomes, and we call that n, our sample size. And this is not like the geometric distribution where we don't know what n is. We keep repeating the experiment there until we get the first success. But with the binomial distribution, we know how many trials there are or how many we're going to do. Of course, the trials are going to be independent, and because they're independent, there will be a constant probability of success for all trials. We're going to define the random variable x as the number of successes out of n trials. So we're counting how many successes we have. Now, don't confuse the word success, how we're using it here, with how we use it normally. If we're interested in studying mortality, then by this definition, success would be death, and of course, none of us, I don't think any of us think that that is a success, and life is as a failure. So success is simply standing for that category we want to study. So the distribution, we'll come up with this distribution. Let's look at what can happen here. If we have x successes, then there are going to be n minus x failures. And that out of n trials, we're going to have the probability of success, we're going to have x of them. And then the failures, there's going to be n minus x of them, so the total is n. And so the probability of getting any one of these combinations of x failures and x successes and n minus x failures is going to be p to the x, q to the n minus x. There are going to be n choose x ways to order them or to choose that many. We don't care about the order here. We just care about the combination. So there's n choose x combinations, ways to do this. So when we take this times this, we get our distribution function. And so let me clean up a little bit so we can see. And so our distribution function, probability distribution function, is here. Don't forget to include your range of x in your, or the support of x. Those x values are very important, okay? So we have n choose x times p raised to the x, q raised to the n minus x. All right. And we will say that x has a binomial distribution. We can write that as x is distributed as a binomial with parameters n and p. We could also use a capital B. I've seen both used, so if you see one or the other, they usually mean the same thing, binomial distribution. So n and p are called our parameters of the distribution because if we know p and q, then we have our distribution, we can define our distribution. So the only thing that would be left unknown in this would be x if we have n and p, because q is 1 minus p. Let's take a look at some of the shapes of the distribution, the binomial distribution. So here is a binomial with n equals 16 and p equals 0.75. You can see that it's slightly skewed, but not much. And as soon as we go to 0.5 for p, we become very symmetric, okay? And as we deviate away from 0.5, here's 0.35, we're slightly skewed. And here is 0.2, we're even more skewed to the right. Whoops, that's not a very good drawing. So we're more skewed to the right here. We're just slightly skewed to the right here, and we're skewed to the left slightly here, okay, for 0.75. So for p above 0.5, we're skewed to the left. For p equal to 0.5, we're symmetric. For p below 0.5, we become skewed to the right. All right, so that's the binomial distribution. That's it for this video. Don't forget to scan and upload your lecture videos before midnight on the date listed on your course calendar. Please be neat because you're your own customer. You can update your formula sheet with this distribution function, or if you have a separate list for different distributions, which I do suggest, then I would update it with that. And next time we'll talk about the mean and the variance and the MGF. So if you have questions, come to virtual office hours. If you can't make those, by all means, email me, but please send me a picture of the problem and your work so I can see what you're doing and how you're approaching it, and I'll be able to help you a lot better that way. Until next time, take care.